Hello and welcome to a paper presentation titled Facilitating Process Reflection in Gameplay Through a Novel Spatio-Temporal Visualization System. My name is Siddartha Maram and I'm a third-year PhD student at the University of California, Santa Cruz. This paper is co-authored by Kleinman, Jennifer Villareale, Jichen, Magy, Seif, El-Nasr. We thank NSF for the generous support, and this paper has been a collaboration effort between three universities such as University of California, Santa Cruz, ITU Copenhagen, and Drexel. Before we dive into the visualization system, we would want to establish motivation in understanding why process reflection in gameplay is important. Today's classrooms are moving from a more textbook and blackboard-centric approach towards a more immersive experience where students engage in a series of activities and games to learn various educational concepts. However, in traditional classrooms, students' performance is heavily parameterized in the form of test scores, homework scores, in-class performance, where a teacher who acts as the knowledge bank is able to judge and gauge the ability and performance of a student. This allows us to plot charts, get visualization systems, develop systems which help students understand where they're standing relative to the class, where they're lacking in performance in a particular area, where they're doing well, and this promotes a much easier form of communication. However, as classrooms go towards a more serious games approach, this is very difficult because the educational concepts are camouflaged within the game, and player moves do not directly indicate the process in which students are learning. It's kind of that it's very hard for teachers to understand why did a particular player make a particular move and where can I point out for them to improve. But this has been different in like AAA games where there's so many parameters for performance such as kill-death ratios, accuracy, win rate, which show where students are standing with respect, where players are standing with respect to their peers, and it's just easier to judge the performance of a esports player. For instance, if you look at this serious game here and somebody's placing some components, it's very hard for us to determine why they've done that and what is the merit or what is the academic drive behind that move. So for this reason, we feel it's important to understand the process in which students are playing a serious game so that it's easier for us to understand where they're going wrong, where they're doing inaccurate moves, where they're doing accuracies, and how can they improve. So in an attempt to understand this better, when we look at previous work in visualization systems within games, a lot of this is focused on AAA games or where there's a lot of kill-death ratio as a primary parameter, or how people navigate the spatial map of the game. So they're like heat maps, they're bar charts, they're node-edge visualization systems, which help you compare how different people have taken different stages of the levels, and in the other parameters could include even biosignals to understand the enjoyment or other metrics of fun within this game. And then similarly, if you move to previous work in learning literature, which talks about visualization systems to help students understand their performance, there have been different attempts at it, such as color bars, where you're trying to determine which range or the bracket in which the student fits compared to his class. There's spider charts which show which areas the student is lacking or needs much more improvement. And then there's peer grading, where you have things like you're showing what percent of students have done better than you or not better than you. So there are different work there, but then there is a definite gap in between how we can bring serious games and visualization systems together to help process reflection. And most of these visualization systems you've seen in learning literature or in game, they do not talk much about the process itself, but they talk about very specific metrics. Magy and Jichen have already worked on coining this term called open player modeling, where you want to model the performance of the player in terms of their process, but not just specific metrics, because this helps understanding their gameplay better and helps reflecting on their playtest so they can do better in subsequent levels. So broadly, we really want to understand how can we develop a visualization system which models player learning in serious games and provides players an opportunity for reflection. So the visualization system essentially has to capture the learning aspect of the game and then prompt reflection. So for that process, we took one game called Play Parallel. It's a very interesting game, and the reason why we chose this game is because it has enough complexity to push people in multiple ways of solving the level. The game is pretty much like how parallel programming is done. You have semaphores and signals, which are analogous to a lock and key. You need to connect your locks and keys to ensure threads, which are processes in computer systems, can do their tasks. So like for example, in this case, this is analogous a bit to the reader-writer problem in operating systems. So the large goal of the player is to place components, like as you see here, like a signal, a semaphore, and then ensure they connect to the right signals and right semaphores by placing them at the appropriate areas so the threads or the arrows can do their job. So there are multiple ways a student can solve this level. They need to know concepts of parallel programming, and it captures the essence of a serious game where you're trying to relate to an in-class concept, but also in a gamified approach where people are thinking critically to solve. However, it is very hard to distill just by looking at the gameplay what a student was trying to do, what was their approach. So that's where we're really aiming to get at. So the methodology that we really adopted has multiple stages. So we're looking at to build a visualization system to help in process reflection. Our first step was a generative step where we're talking to students to understand where they would like help in reflection and what are areas they would want to dive deeper while looking at their play trace. Next, we consulted OLM literature to see what current learning literature has in terms of creating this visualization systems. And something we borrow there is the social models, where we want to use peers and looking at peer data to help self-reflection. Then we also spoke to domain-specific stakeholders, such as the faculty and teachers who teach parallel programming, to understand how they would evaluate a game if they didn't have to do it at scale, what are parameters they look at while teaching parallel programming to understand the performance of the student. So we wanted to incorporate all of this into our design. So this actually acts as a requirement collection step. So then we did an iterative design and development with a mini playtest, trying to understand what is working, what is not working, and what are things we can borrow from OLM literature. And finally, we built the visualization system. We had it in front of a couple of users, a couple of players and students, and we collected feedback and see how the visualization system is actually helping students look at their play trace and improve. So as part of the requirements collection, we did two steps. One was the interviews with faculty and playtest with the students, right? So when we spoke with faculty, so we spoke with two faculty members, and then we transcribed their interviews, and we identified 4 large themes and how they look at the gameplay. One is, once you have the entire play trace, faculty start looking at portions of the play trace. So they break down the play trace to understand what they're doing in each part. Second, they identify how students are placing the components at different areas of the map. So how are students utilizing or identifying the important spatial zones? And the third one was comparing parts of the play trace. So when I had when we had like 2 players play traces in front of the student, in front of the faculty, we could see faculty looking at why one play trace was better, what about that play trace was something the other student could learn. And finally, since you're looking at 2 or more play traces, you can rank these players based on some metrics, such as how quickly they've identified the critical section, or what is the size of the critical section, which are much more related to the game rather than, which is not something you would see while programming, but these are inherent concepts you want the student to learn, which are shown through the game. So the second part of it was doing a playtest with the students, and this has actually already been accepted at FTG, which was led by Jen. We're trying to integrate perspectives of students while they're reflecting or making systems for games. So we had 2 personas after we have done interviews with 10 of the students to understand what they want from a visualization system, which helps them in process reflection. So we had 2 personas. Broadly, these 2 people really wanted to see a high-level view of the community to help understand where they stand, so relatively position themselves with respect to their peers. And this was followed by how they, once they understand where they're with respect to their peers, can they compare data across multiple views, like the length of the play trace, or which part of the board did they use better, and of course which results in wanting them to see suggestions on how they can improve their solutions. So these are the 3 broad pillars in which students wanted help from the visualization system. So using these 2 requirements, we went ahead with the development of the system. So the first thing was developing the spatial abstraction, which was mentioned by the faculty, where you're trying to break the board and not looking at it as a whole, but breaking it down into smaller components, and each component of that board, which we call zones, has a specific role. For example, here zones such as A, K, G, H are very local to one of the threads. That is, only that thread passes through these zones, and the pink thread does not. And similarly, there are zones which are shared, and which is also known as the critical sections. So this is knowledge we've gained from the experts while talking with them in terms of how students should be utilizing the board in a very specific way and not just look at it as a whole. So the way we develop the learner model is, in case a student places a component here and then attaches it to the switch here, we know from the knowledge map that that move is inaccurate because we've talked to faculty and we know how the students are supposed to use the zones, and every time they use the zones wrong, we can identify areas they can improve on, and we have like some set of recommended moves which were given by the faculty, and this helps us like compare where the student is strong and what are the moves they need to look at to improve. So for example, if this player has made a move between dy, there are 4 other ways in which the student could have solved this inaccurate move and actually gone towards a more solution providing approach. So we have a knowledge bank developed in collaboration with the faculty, and this really helps us to develop the learner model and see what is good, what is wrong for each student. Now the second part is how do I compare the second part of the learn model is like we are able to identify what are the inaccurate moves, but we also want to like recommend the good moves. So since each player's board is now seen as a combination of zones, we know which players have actually used the zones correctly and which players could be recommended. So for instance, here the links marked in red are inaccurate, and the student struggles to understand the critical section. So what we do is we have in our learning model that these are the other 2 recommendations the students can actually use, and these are 2 other players who have actually used this particular move in a much more accurate way. So just to understand, so we have the spatial abstraction, we have a knowledge bank which tells which move is good, what are the moves that can be recommended, which move is bad, and what are the moves that can be recommended. So while we cannot look at this board to compare directly with students, what we've done is we've developed a spatial abstraction where instead of looking at this board as just a game arena, we look at it as a graph which is represented by an adjacency matrix, or what we call a game state embedding. This embedding essentially captures the current situation of the board. For instance, you can see one signal connected to a semaphore here, so that is AJ, and in this case you can see AJ has 1 unit there. So the representation of the board in the form of this embedding allows us to develop a vector to represent each state in the game which a player plays. So with this particular embedding developed, it is now easy for us to compare two boards to understand how similar they are, how similar they are not, because it just becomes a dot product or a cosine, taking the cosine between these two vectors to see how similar they are. So essentially what we do is once a player submits a play trace, we break the play trace, which was part of the first recommendation from the faculty. We apply zones, which was the second recommendation from the faculty. We identify the links and how students are connecting or how students are utilizing the zones. We compare against the knowledge map, which was the third recommendation by the faculty. And then we return a list of players which the student can improve upon, because we know what are the moves the student needs to learn to improve. But then once we have the list of board states which the student can improve, we do a ranking based on the embedding. Finally, to design the visualization system, we took the Schneiderman approach, which is very popular in OLM literature, which has 3 steps. Which does an overview first, zoom and filter, details on demand. When we do overview first, we did start with chord diagrams and radial diagrams, but we realized that this is not convenient and students are struggling. And we stuck to a very simple approach where students can see where they stand relative to their peers. So ideally, essentially answering where do I stand with respect to my peers, whom can I look to improve. In this case, you really want to be somewhere close to the center where there's a minimal wait time for your thread and you use the critical sections better. The second step was, can I look at those specific players that help me improve? So the personas really wanted to look at players, how they can improve. For this, we laid out a student's play trace and we marked out which moves were accurate or inaccurate. And they can click below on this plus sign to look at other players and how they have approached a problematic move or how they've approached a good move. So they're looking at very specific parts or specific players they can improve upon. But we also want to understand what about that move was important. So we provide a visualization where we show the current board state of the player, and as they select the different players they want to view, we highlight what about their move was good, and we give 2 texts which says this is what you need to look at and this is how this player has done better, kind of providing more details and why and how they can improve. So combining all these 3 together, what happens is you have this visualization system where the left hand corner is your own play trace or your own board state, and the right hand corner is your peer's board state, and then you have your play trace where you can look at it and you can click on the plus sign to see how other players have done and see how the visualization system really helps you reflect. So as a starter, we also have a during gameplay visualization where students can use pretty much the same concept while playing the game, just in case they're stuck. So we did an evaluation where we invited 8 people to play this game, and they were asked to think out aloud, play the tutorial levels, and use the visualization systems whose interviews we transcribed, and then we did open coding with an IRR of 0.79. So we identified 3 major things. One, how do we selectively filter and present peer data to allow players to gain insights? So we saw students really wanted to optimize their solutions, and in that process of optimizing their solution, we've seen a feeling of competition, like they want to look why particular player did better than them. And in that process of understanding the competition, they realized that they needed to use the spatial abstraction much better. Now, so then if you're able to see reflection, then what are learning opportunities which they can use? For example, the OPM effectively captures the process. Like the students mentioned how the OPM effectively captures the process of them and their peers. It would help them identify new critical sections because they're also looking at the spatial zones and how the spatial zones are being coordinated. And while looking at this, the learning opportunity really which came out was how they're moving from a sequential approach to a parallel thinking approach. For instance, you can see here they've placed 2 signals connecting to one component, but while they are using the OLM during the gameplay, they've had one recommendation which says you can do this better, which they adhere to, but post gameplay they've learned 3 other ways of solving the same thing, where they're now really moving from a sequential approach of using 2 components to one component in multiple ways. So that was a learning we've learned. And similarly, like in a player here, this player is trying to control one thread on its own, but in parallel programming you want to control other people's threads. That's how parallel programming works. So they move from a sequential approach during gameplay, and post gameplay we reinforce that concept. And finally, how do people interact with the OLM? We see people comparing and contrasting recommendations. They're open to share the data with the community. And finally, they're also simulating recommendations based on what the suggestions the visualization system gives. So yeah, these are the 10 large components. So the bigger picture is we have reasons for students interacting with the visualization system, which is ideally they want to optimize their solution. In the process of optimizing their solution, they find competition which they can look upon, and they compare and contrast their solutions and to the recommendations which have come from the competition. And since the OPM effectively captures this process, comparing is much more easier. They can simulate the process because the recommendation highlight what to think about. And in that process of simulating recommendations, you see students utilizing the spatial abstraction to identify new critical sections, which improves their thinking from sequential to parallel thinking, and then eventually resulting in them being okay with sharing the data with the community. The implications of this work lie for both OLM literature as well as serious games literature, and towards the parallel research platform as well. OLM literature, because as open learner modeling has to transform towards open game-based learning, and in that process, how do we judge students' performance? So, we move from OLMs and towards OPMs. And when it comes to visualization systems itself, we are wanting to support process-based reflection rather than metric-based reflection. So that's a contribution we want to make. And then Parallel has been around as a game for 10 years, and there's so much work on it. And since the variety of the game and its ability to be used and incorporated in curriculums, we see this as a very good stepping stone to push the use of Parallel and other serious games in classrooms. But that'll be all from my side. Thank you so much for joining us. Feel free to reach out to me on email or on Twitter at Siddartha Maram. Thanks so much.